Section 5.4 is the fundamental theorem of calculus. Sounds kind of important, right? It's the fundamental theorem of calculus. We're taking a calculus course, so yes, of course, this is a very, very important section and a very important theorem for us to use. But what is it going to do? What it's going to do is teach us how to find the area beneath the curve, how to evaluate definite integrals without having to do areas of rectangles, triangles, semicircles, any of those dang shapes that we've been using in this last two sections. So essentially, the last two sections were the building blocks to what we can conclude in this section. So let's get started. It says you've now been introduced to two major branches of calculus: differential calculus, which was introduced with the tangent line problem, and then integral calculus, which was introduced with the area problem. So far, these two problems might seem unrelated, but there is a very close connection. So there is a close connection between derivative, tangent line problems and area problems, believe it or not. It says the connection was discovered independently by Isaac Newton and Gottfried Leibniz, I think is what it is, and is stated in the fundamental theorem of calculus. Informally, the theorem states that the differentiation and definite integration are inverse operations, in the same sense that division and multiplication are inverse operations. So what does it say? It says if a function f is continuous, and I'm going to call this lowercase f, right, is continuous on the closed interval ab, and the parent function capital F, which remember is the antiderivative of lowercase f, on the interval closed interval ab, then how do we find that area beneath the curve? What you do is you integrate it and find the parent function, and then you plug in the upper limit minus the lower limit. So integrate first, just like you would if it was an indefinite integral. Plug in the upper limit minus the lower limit, and you're done. So it says to use the FTC, the fundamental theorem of calculus, the first thing you're going to do is evaluate the integral. It, just as you would if it was an indefinite integral, except you do not need to add the plus c for definite integrals. Our answer is not going to be in terms of x's. Our answer is going to be a number. And then the second thing you do is you evaluate it at the upper limits and the lower limits. And you always want to do the upper minus the lower. You always want to do the upper minus the lower. So for instance, it gives us an example here, a nice example. It says, what if we wanted to find the integral from 1 to 3 of x cubed dx? So this is the area beneath the curve of x cubed from x equals 1 to x equals 3. How would we find that area? Well, we don't have to do limits, we don't have to do rectangles, we don't have to look at the shape, nothing. All we have to do is integrate it. So imagine that 1 and that 3 weren't there. Use the power rule. The integral of x cubed is x to the 4th over 4. So that it would be plus c, but we don't have to use the plus c anymore. But we still have to evaluate it from the numbers 1 to 3. So what do? We take the answer, which was x to the 4th over 4. We plug in the upper limit, which is 3, so that would be 3 to the 4th over 4, minus we plug in the lower limit, so that would be 1 to the 4th over 4. So that's 81 fourths. 3 to the 4th is 81, and 1 to the 4th is 1. So that's 81 fourths minus 1 fourths, which would be 80 fourths, which simplifies to 20. So what's the area beneath the curve of x cubed on the interval 1 to 3? The answer is 20. We just found a very simple, easy way to connect the idea of area, the idea of derivatives and antiderivatives, and put it all together, and we are now able to find the area of a shape that has nothing to do with rectangles, triangles, anything, semicircles. We can find the area of any curve extremely quickly. Integrate it like you would it's an indefinite integral, plug in the upper limit, plug in the lower limit. Again, if your integral has numbers on it, that's called a definite integral. If your integral has numbers, your answer is a number. If your integral does not have numbers, your answer has x's or whatever the variable is and plus c. If it has numbers, answer's a number. If it doesn't have numbers, if the integral doesn't have numbers, you're going to have x's and c plus c in your answer.